In this presentation, we're going to look at sequences and series, and we're going to tackle a problem with sequences and series. Didn't mean to do that. So what I meant to do is go on to the next slide and look at the problem. Now, this is a screen grab from a book or a PDF. Anyway, the number of fleas in a carpet is 10,000 at the start of 2007. Each year, 5% of the fleas die and 2,000 are born. Find an expression in as simple a form as possible for the number of fleas n years after the start of 2007. What happens to the number of fleas in the long run? Right, well, this is quite a complex question, but one thing I'm going to sort of point out is that we're going to have a geometric series as part of this. And this is the formula for the geometric series, where we have A as a sort of scaling term, R is a common ratio, and K is just a sort of indexed value here. For example, A, oops, plus AR, where that's the ratio, plus all the way up to AR n minus 1. So a little quick example of that might be, no, I won't do it. I was going to sort of spoil all the fun. Anyway, it actually works out to be this expression here. Okay, so that so far so good. Now let's go back to the problem. The number of fleas in the carpet is 10,000 at the start of 2007. Just so you notice, actually, this starts here at k is equal to 0. So we're going to work on that basis here, that the starting point is time 0. Okay? So the start of 2007 is, we're going to call that year 0. Now each year 5% of the fleas die and 2,000 are born. Okay, so let's start of like putting this information together. So year 0, we have 10,000 fleas. Year 1, which is the following 1 year later, we have, well, if 5% die, that means 95% of the original 10,000 are there. Okay. But that's not all. We are actually additionally told that 2,000 are born. So it's a constant increase of 2,000. Okay. Year 1, that's year 1. Let's have a look quickly at year 2. And I'm going to put this in a different color. So 0.95 of whatever there was the year before. So I'm just going to put this in the year 1 value, y1, plus 2,000. Okay, but the year 1 value is, what do we have from year 1? We have 0.95 times this expression up here, which I'm going to put in blue. So I'm going to keep this in blue. 0.95 by 10,000 plus 2,000, and put the rest in black, plus 2,000 again. Okay, let's work that out a bit. I'll keep this in black here again. So this is 0.95 squared by 10,000 plus 0.95 by 2,000 plus 2000. Okay. Now, we're going to use this here as the basis of an answer. So I'm going to quickly put in the equivalent. If you were to do the same thing out again for year 3, I'm not going to rationalize it. What I'm going to do here is just to sort of write down, just for the sake of time, I'm going to write down what it would be. So for year 3, it would be this. It's just doing the same process again, but it's just if I was to talk through it, it would be just overkill. 0.95 cubed by 10,000 plus 2,000 plus 0.95 times 2,000 plus 0.95 squared times 2,000. So what I'm going to do here is write out a general expression for year n. And that is, this is an important bit now, 0.95 to the power of n by 10,000 plus 2,000 plus 0.95 2,000 and so on, all the way up to 0.95 to the power of n minus 1 times 2,000. Okay. So I've broken it up deliberately into two parts. I have this part here, the top line there, and this second line here. Okay. Now, the top part there is pretty much good to go. We're finished with that part. It's the second part is actually more interesting. So everything I have below on the second line there is pretty interesting because we can actually state that this is a geometric series. Okay, and within it, A is 2,000. R, the common ratio, is 0.95, and it goes from 0 to n minus 1. So this is where the index term here is just r to the power of 0. It's just 2,000. Here it's n minus 1. So it actually fits in with the equation we have previously. So let's go back to that equation, and there we have it there. So this is how we could sort of encapsulate this into one equation. N minus 1 from k equals 0 of 2,000 by 0.95 to the power of k. Just like we had in the last. That's how we sort of might write it out mathematically. So that's 2,000 all over 1 minus 0.5 to the power of n all over 1 minus 0.95. Now that actually works out, the 1 minus 0.95, I'll just write it up here at the top, that is equal to 0.5. Okay, so let's get rid of that here, and just more so for the sake of space, and just replace that with temporarily with 0.05. Now we're dividing 2,000 by 0.05, and that's essentially, if you just work that out in your calculator, that actually works out to be 40,000. So I'm going to get rid of this again. I'll just be clear about what I'm doing there. 2,000 divided by 0.05 works out to be 40,000. Okay, so we could just put that in there. So we'll get rid of this fraction altogether and put in 40,000 there instead. So 40,000 by 1 minus 0.95 to the power of n. Okay, just as a sort of important remark, the n only the power of n is only for 0.95, that is, it's at the power of n. All right, so that is the geometric series, which was the second part of the expression. Where am I? Sorry, I'm just going back there. So that was the geometric, was only the second part. The top part was not part of that geometric expression. It was a separate part. So essentially what we have to do is put them both together. And so in the long term, the y of n, the population in year n, will work out to be 10,000 by 0.95 to the power of n plus 40,000. Sorry, I'm just be clear. Capital N is what we were asked from the question. Plus 40,000 by 1 minus 0.95 to the power of n. Okay, so that's as simple as we can make the expression. And, well, actually, no, we can go one step beyond. We can actually just bring in we can make it a little bit easier, actually. So we have 40,000 minus 40,000 0.95 to the power of n plus 10,000 0.95 to the power of n. So I'm getting cramped for space here. And so essentially what I'm saying is that we can actually just simplify it a little bit more. Actually, just cop that, we can go a little bit further with it. And that's 40,000 minus 30,000 0.95 to the power of n. Now, I don't see any further ways we can simplify that, so I'm going to call that my final answer. That's as simple as we can get the expression. In year n, what is the population of fleas on this carpet? Just as a remark, n is a large number. As n gets large, (0.95 to the power of n gets really, really small. And in fact, it goes to 0. Okay, so in the long run, as n gets larger and larger, 0.95 to the power of n becomes 0. And it's essentially in the long term, this entire expression will just converge to 40,000, because 30,000 times 0 is just 0. So in the long term, the y of n is going to converge to 40,000. Okay. So that's the end of the presentation.